Hello and welcome. For this video we are going to look at atoms and radiation, and we're going to look at uses and dangers of nuclear radiation. Now, just as a brief recap, we've got three types of radiation that we've talked about in the past. We've got a video out, I've done a video about these three already, so you can look back and look at the details of those. But for the moment we have alpha radiation, that's shown by this little alpha sign. It's made of two protons and two neutrons, as discussed before. We've got beta radiation, which is just an electron. The sign for beta is this B letter with a slightly longer tail, and gamma radiation, which is actually an electromagnetic wave. It's not a particle, it's an energy wave, and it's shown by this little symbol here. Now, there are certain dangers of these three types of radiation, and the first one is that they can be what we call ionizing. They can ionize, and they ionize to different amounts each. So let's have a look at what we mean by ionizing. Here we've got an atom, and in the atom, as we've studied before, we've got a nucleus with a positive charge, and we've got electrons flying around on the shells around the outside, different shells with electrons on, and the number of electrons balances out the number of protons in the nucleus for a stable and neutral atom. Now, what can happen with nuclear radiation is if we get either alpha, beta or gamma radiation coming into contact with atoms, and particularly atoms in the body, you might get this effect of ionization or ionizing. Now, this is most pronounced, or happens most, with alpha radiation. Now, what could possibly happen is an alpha particle comes along, it actually collides with an electron in one of the shells, and it knocks that electron away from the shell. And so what's happened is you now have one less electron for this atom, and that means the electron gains a positive charge, and that atom has been ionized. Now, if atoms in the body become ionized, that means that the way they react with other atoms in the body or other molecules is going to change, and that can actually cause problems within the body. If atoms in the DNA become ionized, that can cause the DNA to not work properly, and in actual fact it can actually cause cancer to occur within the cell and then possibly spread throughout the body. So one cause of, or one danger of radiation, is the fact that it can cause cancer in the body. Now, while alpha particles are quite strongly ionizing compared to the other two, beta particles are less ionizing, because the beta particle is actually an electron, and electrons are much smaller. This is actually not drawn to scale, but electrons are much smaller than the alpha particles, and they are much less likely to hit the electrons in the shells. Now, while they are much less likely to hit electrons in the shells, you must be aware that they actually can penetrate through much more than alpha particles can, so therefore they go through more atoms, and there's a slight increased risk of them being able to ionize atoms simply because they're going through more atoms. In terms of gamma rays, these are the least ionizing of the three. That's simply because they are energy waves, and they are less likely to hit electrons with enough energy to knock them off their orbitals and therefore cause the atom to become an ion. So the key points here are that we have alpha radiation, that's the most ionizing, beta radiation, which is less ionizing, and gamma radiation, which is the least out of the three. Now, it's worth mentioning here the idea of the penetration power of the different kinds of radiation. So alpha radiation can actually be stopped by skin. The particles of alpha radiation can be stopped by skin, or actually can just be stopped by paper, so they won't actually get through skin or get through paper. So while they are strongly ionizing, they are unlikely to be able to get into the body to be able to do that damage, because the skin will stop them. This becomes a problem, in fact, when alpha radiation actually gets inside the body. If it manages to get inside the body, you're going to get a lot of ionization of cells, and that's where it becomes very dangerous. In terms of beta particles, well, they can travel straight through paper, they can travel straight through your hand. They will require a couple of millimeters of foil to stop them, and that will be enough to stop them, but they will get through hand and paper. And in terms of gamma rays, well, they can get through your hand, get through paper, they can even get through lead, and you'd need a very thick slab of lead in order to stop gamma radiation, and even then it's not guaranteed that it will stop all of it. Okay, so these penetrating powers are quite important, because we're going to look at some of the uses of radiation, and you're going to be able to, or you should be able to, use this idea to be able to choose a type of radiation for a particular use. So here's an overview of the different kinds of uses. We've got gamma radiation, which is used to sterilize surgical equipment, so equipment that's used to carry out surgery in hospitals. Gamma rays can be fired at these, and that will kill the bacteria that are on the different instruments. It can be used to kill cancer cells, so something called radiotherapy uses gamma rays to point at a tumor that might be in the body, and if it's done carefully and aimed carefully, it can kill the cancer cells without doing harm to the cells around the cancer cells. It can also be used as what we call tracers, and we'll look at that in a bit more detail in a minute. Alpha cells, or alpha particles, sorry, they can be used for controlling paper thickness, and they can be used in smoke alarms, and we'll look at those two in a moment. We have other uses of nuclear radiation, and that's radioactive dating. We can use the idea of half-lives to predict the age of, or to calculate the age of different materials. And for beta particles, we can use it for controlling foil thickness. So it's a very similar idea to controlling paper thickness, but we use it for controlling the thickness of foil that's made in factories. So let's look at some of these in a little bit more detail. The first example here is to control paper thickness. Now, in the final stages of the production of paper, the paper is made into sheets that are the right thickness for the job. And the way this is done is an automatic method, and they use alpha radiation. So here is our source of alpha radiation, and alpha particles are being passed or being shot at the piece of paper that's coming off this roller. Now, if this paper is too thin, what happens is alpha particles get through, and this detector on the other side will send a signal to a processor that will cause these rollers to loosen up a little bit. So that means the paper will be a little bit thicker. That means less of the particles will get through, and that then we know it's the correct thickness. If, however, no particles get through at all, we know the paper is a little bit too thick, and therefore these rollers can be caused by the detector and the processor to squeeze tightly against the paper, or more tightly against the paper. More alpha particles will get through, or the right amount will get through, and we know the paper is the right thickness. So in that way, these rollers adjust the thickness, or adjust the pressure that they put on the paper in order to make it the right thickness that they want it to be. And this is all done by alpha particles in a detector and a processor. Another example of the use of radiation is for tracers. Now, this person here has taken a dose of a drink that contains a radioactive source. Now, that radioactive source can travel through the blood around the body, and if there's a particular point where there's, say, a tumor or damage inside that's causing an accumulation of blood, this can be detected by a detector. Now, this type of the type of radiation that we use here is going to be gamma, and it's very important that it has a very short half-life. That means it will lose its radiation very quickly, and the reason why we need to have a short half-life is because we want it in the body for a short amount of time as possible. While it's gamma radiation and it's not re-ionizing, we still don't want it around for too long, so it has to have a short half-life. We can't use alpha radiation sources for this because they will ionize in the body and cause a lot of problems. Beta particles may not be able to get out of the body, and they are slightly more ionizing than gamma, so in this case we use gamma. Going back to this example, which I forgot to mention, we actually use alpha radiation for controlling paper thickness, because if we use beta radiation, that can get through paper quite easily and it wouldn't do the job. We do actually use beta radiation for controlling the thickness of aluminium foil that's produced in factories. And it's the same idea as here, except we've got foil and we've got a beta radiation source. The next use is for, again, it's for tracers, and here we've got a pipeline that's sprung a leak. So this is a water pipe, and it's sprung a leak, but the engineer doesn't know where it's sprung a leak, and it could take a long time and lots of money to dig up whole long roads or whole long bits of land just to find where the leak is. But if we inject a source of gamma radiation into the pipe, what can happen is where the pipe is leaking, the water with the gamma radiation, it will accumulate, and the little man can come along, and he can find out exactly where the leak is, and the detector will tell him where there's a large dose of radiation and therefore where that leak is, and so he can find the leak. Again, important to use gamma radiation. If you used alpha radiation, it wouldn't work because the alpha radiation wouldn't be able to penetrate through the soil. Beta radiation again wouldn't penetrate through the soil, but alpha radiation can. Sorry, gamma radiation can. Now again, it's important that this has a very short half-life, so it's not around in the environment for very long at all, but it's the gamma radiation that we use. The last example is a smoke detector, and this is reasonably complicated, but the basic idea is that we have alpha particles being shot across a gap. They will ionize the air. They will ionize particles in the air, which will then allow a current to flow, and if there is smoke, if there's a fire and smoke comes along, that smoke will absorb the alpha particles. They will no longer be able to ionize the air, and therefore the alarm will be triggered to go off. Okay, so here are some uses of different types of radiation. What you should be able to do is to decide which kind of radiation is most appropriate, and that's to do with how dangerous it might be, and also how long we want it to last. So short half-lives are required for tracers and for gamma radiation in these pipes. We want very long half-lives for controlling paper thickness, because we want this to last as long as possible. We don't want to keep having to buy new sources of radiation or radioactive materials for this. And again, for the smoke alarm, we want to have a very long half-life so that we don't have to keep replacing the radioactive material in the smoke alarm. So we have to be able to choose which type of radiation is best for the use, and the reasons we might give are how long the half-life should be and how dangerous the radiation might be in the particular use that we are talking about. Okay, so that's an overview of the safety and danger of using radioactive materials. That's me done for this video. Thanks for watching, and I'll see you again soon.